Hello all of you. Welcome to the 40th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been discussing about graph theory applied to chemical engineering. And in the last class, we started the decomposition of large scale linear systems, trying to figure out the priority order of solving material balance equations on a graph or a flow sheet. So, here we are so far. So, we started with this particular flow sheet, and this is the algorithm that we have developed so far. In step 1 of the algorithm, we look for the columns in the Boolean matrix R containing all zeros. They refer to the vertices without any ancestors, and these balances has to be done first or after the others found first in the earlier steps, because we will always return to step 1 after every step of the algorithm. Then in step 2, we delete the vertices identified in step 1 and all its edges from the graph. That means we basically delete the rows and the columns corresponding to the vertex or vertices identified in the graph. And then we always go back to step 1 if there are columns found with all zeros in the graph after reduction, right. It may so happen, like in this case, what happened is, in the beginning we figured that 1 and 4 are the vertices having no ancestors, but after we deleted 1 and 4, we saw that 5 is the vertex containing no ancestors now. So, first we did 1, then 4 in any order, and then we did 5, and now we basically again look for vertices containing no ancestors, and then there were none, right. So, then we move to the next step. The next step was to look for rows in the reduced matrix. Keep in mind that whenever I say R, that is the after reduction. After every step, I am deleting the rows and columns. So, whatever R remaining is there, that is what I am referring to. So, look for the rows in R containing all zeros, and that means the vertices with no descendants. In this case, we figured that 9 and 10 are the vertices with no descendants, and these balances has to be done last, or by the same logic before whatever is found last in the earlier step. In this case, it did not happen, but in general it may also happen that after deleting 9 and 10, there may be another vertex coming up, popping up, that is now having no descendants. In that case, that will become second last before the 9 and 10 balances. And then again, whatever I did for the step 2, I delete the vertices and all its edges. That means deleting the rows and columns corresponding to the vertex in the graph. And again, we go back to step 1 always if there are columns found with all zeros, or go to step 3 if there are rows found with all zeros, and then we only go further if none of that is possible, right. So, this is what we did. So, in the first step, we deleted the vertex 1 and 4 because they did not have any ancestors. Then I was left with this graph, this reduced graph, and now by the logic that I just said, vertex with no ancestors, now we have 5 with no ancestors. So, we do 5 after this, and we update our priority order scheme, first 1 and 4, then 5, then we delete 5 and the corresponding is, like here we delete 1 and 4 and all the corresponding edges, and then I have a new reduced graph. And now we can see in the reduced graph there is no vertex here, which is having no ancestors. So, then we look for vertices with no descendants, and we see these are 9 and 10. So, we delete 9 and 10 from there and all the edges corresponding to 9 and 10, and we keep them for solution towards the end. And then I am left with now this reduced graph that only contains the cyclical nets. In this case, we have 2 cyclical nets. One is order 2, that is 2, 3, and other is order 3, that is 6, 7, 8, and both are maximal because they do not share any common node, right? Of course, they are not subset of each other, but they do not share any common node. So, both of these cyclical nets are maximal. Okay, so this is my reduced graph, and I can quickly write down the Boolean matrix. From 2, I can go to 3 in one step. From 3, I can go to 2 and 6. From 6, I can go to 7. From 7, I can go to 8. And from 8, I can go to 6. So, what should be my next step? The next step is we now compute the R square. And what the R square will tell you is whether we have cyclical nets of order 2, right? If you have a cyclical net of order 2, what should happen in that case? What should happen is that I should reach the same vertex in 2 steps. Let us say 2, 3 is a cyclical net. So, I can come back to 2 in 2 steps. I can come back to 3 in 2 steps, right? And therefore, the diagonal terms corresponding to 2 and 3 should become 1 in R square. So, in 2 step, I am visiting the same vertex, right? Of course, I have told you that the better way of doing cyclical nets in the graph is to compute R star and do intersection with R star transpose. But this becomes easier because we can compute R, R square, R cube and so on in succession, and for decomposition scheme we basically find the cyclical nets in this particular way, right. So, let me quickly write the R here. So, from 2 I can go to 3, from 3 I can go to 2 and 6, and from 6 I can go to 7, from 7 I can go to 8, and from 8 I can go to 6, right. So, if I multiply R with the rule I have said is I basically have to multiply rows with columns. So, for the first row, second element is 1, second element is 1 for the first and third column in the graph. So, I put a 1 here and 1 here. So, I can go from 2 to 2 in 2 steps and 2 to 6 also in 2 steps. Similarly, for second row, we have first and third element is 1. First or third element is 1 for the second column here and the fourth column here. So, from 3 I can go to 3 in 2 steps, or I can go to 7 via 6, 3 to 6, 6 to 7. And from 6 again, the third row has fourth element as 1. So, I look for the column containing fourth element as 1, that is the last column. So, from 6 I can go to 8 in 2 steps, and then for 7 the last element has to be 1, that is true for the third column, and for 8 the third element has to be 1, which is true for the fourth column. So, basically now we have kind of a scheme to basically figure out what is happening in 2 steps, and if the diagonal terms are 1, it basically means that there is a cyclical net. If at all I can revisit the same vertex in 2 steps, that means that there is an order 2 cyclical net. But then what we do is we see whether this cyclical net we have identified, this 2, 3 cyclical net, does it have any ancestor or does it have any descendants, right. How do we locate the ancestors or descendants? As we have done, ancestors are along the column and descendants are along the rows. So, for 2, 3, the blue cells here identify the ancestors of 2, 3 and there are none. So, 2, 3 does not have any ancestor apart from 2, 3 itself in the graph. So, therefore, this 2, 3 balances should be solved first or after whatever is found first. So, we already have figured out that 1, 4 and 5 has to be done first. So, this will come after that. And what is also important is the balance of 2 and 3, because its cyclical net has to be done simultaneously, right. So, in summary, we locate using R square the cyclical nets of order 2, which is going to be also maximal, with either no ancestors or no descendants. If there are no ancestors, which is this case, then in that case we will solve it first, or whatever has been after whatever has been found first, and it has to be done simultaneously because it's cyclical net. If on the other hand, which is not the case here, if we find that this cyclical net does not have any descendants, then we keep it for the last or before whatever has been found last. But in this case, we find that 2, 3 is a cyclical net of order 2 and it does not have any ancestors, that is the blue cells here. So now we have figured out a scheme. So we have 1, 4, 5 to be done first and then 2, 3 simultaneously. So we have figured out that we have a cyclical net here, and now I am left with pretty much the graph containing only 6, 7, 8, right. But again, as a matter of programming, we always go back to the earlier step, right. So we delete this rows and columns corresponding to 2 and 3 now from the graph, right, and that correspond to deleting these vertices and all these edges starting from 2 and 3, and we look at the remaining graph. We look at the remaining graph and do its Boolean matrix. So we see from 6 I can go to 7, from 7 I can go to 8, and from 8 I can go to 6. So this is my reduced Boolean matrix now. We see again, are there now any columns containing all zeros? There are none. Are there any rows containing all zero? There are none. Are there any cyclical net of order 2 with no ancestors or no descendants? In order to figure that out, we have to compute the R square, and we can do that. So for the first row, second element is 1, second element is 1 for the third column. Then for 7, the third element is 1, the third element is 1 for the first column. And for 8, the first element is 1 and first element is 1 for the second column. So we do not locate anything along the diagonals. That means we do not have any order 2 cyclical net, which is pretty much apparent from the reduced graph. So what do we do next? We go ahead and look for maximal cyclical nets of order 3 with no ancestors and no descendants, right. So now I am left with only this graph 6, 7, 8. These rows and columns are already gone, right. And if you do the R cube here, what you will see is that you are going to have ones along the diagonals. Why? Because from 6 I can come back to 6 in 3 steps, first to 7, then to 8, and then to 6. From 7 again I can do the loop, come back to 7 in 3 steps. From 8 again I can come back to 8 in 3 steps. So we locate that we have an order 3 cyclical net 6, 7, 8, and since now there is nothing else left in the graph, these are the vertices without any ancestors, without any descendants, and their balances has to be done first or last, does not matter. This is going to be after whatever has been found first or before whatever has been found last, right. So therefore the scheme, the final scheme we have is this. We solve the balance of 1 first, then 4 and 5, and these 3 can be in any, and the first 2 can be in any order. The first 2 can be in any order because they were figured out first, then 5, then 2, 3 simultaneously, then 6, 7, 8 simultaneously, and 9, 10 again in any order. So you see, we can therefore develop basically a solution scheme for solving the balance equations for this graph, and the fundamental idea that goes behind it is it tries to identify the cyclical nets in the graph, which are the ones which has to be done simultaneously, and that is where the computational effort is going to be more, so as to speak, right. So therefore, if we have to, for example, solve the 10 balance equations, and if it has to be done simultaneously, you can imagine that it is going to be more computational effort than compared to solving 2 equations simultaneously or 3 equations simultaneously, right. Because every other step we are solving just one equation. Only in step 4 and 5 here we are solving 2 or 3 equations simultaneously. That is clearly better than solving all 10 simultaneously, right. You can imagine it is a linear system. So we can solve it by writing some kind of a linear equation of the form Ax equal to B. In this case, A is my augmented incidence matrix, X is my column vector containing all edges, and B is basically a null vector, right. So, as it stands, I have to basically compute something like inverse of A, right. So, computing a matrix inverse of a 10 by 10 matrix must be more difficult compared to doing a matrix inverse of 2 by 2 matrix or 3 by 3 matrix. And now extend this idea to like a much bigger flow sheet. And now you see the advantage of doing that. Let's say if you have thousands of units in the flow sheet, and once you are feeding in the computer, you don't have an intuitive way of seeing it as I had that possibility here because I can see the graph and I can analyze it. But for 1000 unit flow sheet, the graph will be highly messy, and therefore it will be very, very difficult to basically figure out where the cyclical nets are and so on, and to come up with a solution scheme even for the overall mass balance, right. But this provides kind of a programming way of implementing it. It will go in these subsequent steps and basically decompose the system to something that is computationally easier to solve. That is the whole idea that we have in the decomposition of the linear systems. So, this is my final solution scheme as we have seen, and we can see it in practice. So, for example, how do I solve 1? I will have the balance of 1. So, y1 minus y12 minus y13 is equal to 0. So, clearly it also depends on, as I said in the very beginning, what is being specified, right, and also tells me what should be specified in some sense, because I want to solve the balance of 1 first. So, I need to know at least 2 of these, right. So, let us demand, for example, that y1 is known to me, which is the input anyway. Input is very intuitive to be known, and y13 is also known, that is bypass. I should know what is the fraction of bypass, and then this will give me my y12. In next step, I do it for 4. For 4, the balance is y4 minus y45. Let us say y4 is known to me, then I can find y45 from here. And now I move to vertex 5, and the balance is y45 minus y56 equal to 0. y45 I have just figured out. So, now I can solve for y56, and then I go ahead and solve the balance of 2 and 3 simultaneously. So, let us write the balance for 2. For 2, we have y12 minus plus y32 minus y23, and for 3 we have y23 plus y13 minus y32 minus y36 is equal to 0. y12 is something we have already figured out in the first step. So, y12 is known to us. y32 and y23 I need to solve for. Again, I can, for example, ask what is the recycle fraction. In this case, y23 may become the known variable, but if it is not, then in that case we have to solve these two simultaneously anyway, right. So, again here we have y23 is also an unknown, y32 is also an unknown, and y36 is also an unknown. y13 is already known to me, right. So basically I can demand, let's say y23 is given to me or y36 is given to me, and in that case I can get the remaining variables from here, right. So this basically guides you that which variables should be specified in order to make the solution solvable as well, apart from giving you a method to attack. It will not always work because you can have a weird choice of input variables. Let us say in the very first step, you don't know any of that y1, y12, y13. In that case, clearly the solution scheme is not very ideal. So we have to tweak this equation a little bit. So it gives you some kind of a guide, and if you have the liberty to kind of choose the input variables or specified variables, this is going to work perfectly. But even otherwise, this will basically help you figure out where is the difficulty in the flow sheet, because you are identifying the cyclical nets, you are identifying which equations therefore has to be done first, which equations has to be done after it, and so on. So it can be serving more as a guide than something like a rigid simulation scheme, right. So let's say, just for the sake of argument, let us say y36 is given to us, then we have simultaneously equation in y23 and y32. So I will solve for y23 and y32, right. So y13 is also given, and y12 we have already figured out, right. So I can solve for y23 and y32 provided y36 is done, and then I am left with the balance equation for 6, 7 and 8, and we have to solve them simultaneously. And then finally we go to the solution of 9 and 10. For 9 the balance is quite straightforward, y89 minus y9 equal to 0. y89 must come from the solution of 6, 7, 8, or it can also be a given variable, it depends on the context, right. But nonetheless, this can be attacked maybe towards the end after we have done that, right. So unless the choice of variable is very weird, or unless you don't have a complete liberty on the choice of variables, this graph theoretical scheme can actually be a very good guide to basically tell you which equations to attack first and which equations to attack next. But keep in mind that this is not something which is a hard and fast rule that will always work. It will figure out the difficulty level, it will tell you a suggestive method, but it is not likely to work always, because there can be some weird choice of input variables where it is not going to work. So with that, I conclude the final decomposition scheme. So we will start with the columns in R containing all zeros. These are the vertices with no ancestors, and we solve these balances first. Once we have figured that out, then we delete the vertices identified here and all its edges from the graph that corresponds to the rows and columns for that vertex. Then once we are not finding any columns further containing all zeros, we move to next step. We look for rows containing all zeros. These are the vertices with no descendants, and we solve them last or before whatever has been found in the earlier steps. Again, we delete the vertex and all the edges from the graph that corresponds to the rows and columns for that vertex in the Boolean matrix. And then again we have a reduced graph. We again go back to the step 1. We look for again the columns containing all zeros. If not, then rows containing all zeros. And eventually I will have a reduced graph that will have neither the rows or the columns containing all zeros. Then we compute the R square, and the diagonal terms in R square will basically tell me whether we have a maximal cyclical net of order 2 in the graph. And then we look in the R matrix in the columns for those vertices and see whether this cyclical net has any ancestors. And then we look also along the rows to figure out if this cyclical net has any ancestors. Descendants. If there are no ancestors, then we solve them first. If there are no descendants, then we solve them last. But what is important is that the equations for these two vertices forming the cyclical net has to be done simultaneously. Again, we delete the vertices identified here. Again, we go back to the step 1. We look for columns containing all zeros. If not, then rows containing all zeros. That's very, very important that we go back after every reduction to the very first step. And then again cyclical nets of order 2 containing no ancestors or no descendants. And then once I am done with that, then we go ahead and look for R cube, and whatever steps I did for R square, I do for R cube as well. This is going to be cyclical nets of order 3. In the particular example that I have taken, we only had cyclical nets of order 2 and 3, but you may expect that in an actual flow sheet you may have even higher order cyclical nets, but the same idea is going to apply. Let us say for order 4 cyclical net, I will compute R to the power 4 and look for columns diagonal containing all ones. For 5 order cyclical net, I will look at to the power 5 and again look at the diagonals containing ones, right? And accordingly, we can keep on doing until we have completely decomposed the graph, and then we have the priority order of solving equations. In the next class, we will take some examples of this approach. So with that, I stop here. Thank you so much.